So in my uh, second part of this lecture, I will now go through the application of quantum mechanics in and also explain the quantum confinement effect in nanoscale materials. So now, first we have to understand what is quantum confinement effect. So what are the reason for the unique optical and electronic property of these quantum dots? Actually, the reason behind this unique optical and electronic properties is the quantum confinement effect, which I mentioned here. And because of that, it shows unique optical and electronic properties. And in previous lecture, I told already that the quantum dots have a versatile application, and it has a very potential application in different fields. So now, what are the advantage of quantum dots over any other fluorophores, conventional fluorophores such as organic dyes, fluorescent protein, lanthanide complex, like that. So first one is that absorption spectra. Quantum dots have generally very strong and broad uh, absorption spectra. It has also very large molar extinction coefficient, and it shows narrow symmetric uh, emission spectra. So these are the very advantage of quantum dots over organic fluorophores. So also that quantum dots have longer lifetime in comparison to the fluorophore. So it shows high quantum yield above 20%, and the important thing is that quantum dots are very photostable. So it it excellent resistant to photo bleaching. This is one of the important point over the organic fluorophores, and you can easily bioconjugate it with various type of molecules, drugs, etc. And this quantum dots are very resistance to the chemical degradation. That means highly chemical inert. So these are the fundamental advantage of quantum dots over other organic fluorophores or other um, fluorescent materials. So now, what is quantum confinement effect? Actually, in bulk semiconductor, here is the bulk semiconductor. In this case, actually charge carriers can freely move in all three directions. So that means your charge carrier or electron behave like a free particle with continuous energy levels and density states. So this shows the continuous energy levels. But when quantum mechanical effect is observed, when a particle motion is restricted in one or more direction. So here particles means electron. So if you can restrict the motion of electron in any one or more dimension, then you will get the quantum confinement effect. So in this case, uh, in a other word, you can say that excitation, that means excitation, what is I already told that what is excitation in previous lecture, that excitation means electron and hole pair. So that is confined in one or more special dimension, then you will get also the quantum confinement effect. So because of that, QD have properties that are between bulk semiconductor and the discrete molecules. Molecules. So that means quantum dots will behave like a in between the bulk semiconductor and discrete molecules. So in case of quantum oil, quantum wire, quantum dots, in every cases you will see at least one direction there is a restriction of movement of electron, and you will get the quantum confinement effect, and because of that you get some beautiful fluorescence property from quantum dots. Also you can categorize quantum confinement effect in three types in quantum structure in semiconductor nanostructure. The first one is quantum oils. This is two dimensional confinement effect, and this is quantum wires. This is one dimensional system, and this is zero dimensional is quantum dots. So you can categorize in a three way this quantum structure in semiconductor structure. So first one is quantum oil. You can see the structure. This is quantum wire, and this is quantum dots. You also apply this Schrodinger wave equation in all three cases, and you can get the carrier wave function in this structure by the solution of time independent Schrodinger wave equation with effective mass approximation. Also you can get the carrier energy levels as well as the corresponding density state from this quantum mechanics theory, quantum mechanical theory. So now, what will be the size of the particle where quantum confinement effect will observe? So, or you can ask like that: how narrow does the nanostructure need to be in order to observe the quantum effect? The answer is, when we confine electron on the scale of their wavelength, we should expect quantum effects. That means your uh, mm, the size should be of the electron de Broglie wavelength. So now the question is, what is the wavelength of the free or mobile electron? So you can calculate the de Broglie wavelength from this equation. Now P is equal to H cross A. You can see that means H cross into 2 pi by lambda B, and E is equal to P square by 2m. That means this is the average thermal energy. That means this is 3 by 2 kBT. From the two equation you can calculate the lambda B. Lambda B means root over 4 pi square H cross square divided by 3 mkBT. So from this equation you can calculate the electron de Broglie wavelength, and that is also depend on this mass of the, you can see that this is one factor is mass of the materials, or mass of the atoms, or mass of the materials. So in case of silicon, the quantum confinement effect observed because the silicon has about 10 nanometer per electron at room temperatures. But for lighter masses, confinement is felt wider oils. So in case of germanium, the mass is less. So because of that, the wavelength will be much bigger. So from that you can calculate, or you can get the information that where confinement effect will observe. So in case of silicon, that the size should be below 10 nanometer, then you will observe the quantum confinement effect. So now we will apply the Schrodinger wave equation to solve these systems. So first we take that electron energy greater than potential energy. So this is the Schrodinger wave equation, that d2 psi x by dx square plus 2m by h square h cross square into e minus v naught psi x is equal to 0. So you already solve it, you know it how to solve it. So we consider that k square is equal to 2m by h cross square into e minus v naught. The equation becomes this, and the solution of this equation is psi x is equal to e to the power plus minus I kx, or you can write psi x is equal to a sin kx plus b cos kx. So you already know that how to normalize, how to solve this wave function in case of one dimensional box. So in this case the equation is this, and you get the solution maybe this one. Now you apply the boundary condition. So before in psi will be 0 at 0, boundary condition 0, and when the length of this box will be L, then psi will be 0. So that will be psi will be 0 outside this box and after the length of box. So you apply that one, and you get, when you solve it, you already know about from your previous module knowledge that how to solve it. You will get the function is, this is psi x is equal to a sin kx, or psi 0 is equal to 0. So when you solve it like that, so you will get kl is equal to n pi. That means k is a quantized where n is equal to 1, 2, 3. So from that you will also get the quantized energy levels. So you see that quantity energy level is given by this equation. So this is En is equal to h cross square into kn square by 2m, or you can write this equation like that: h cross square n square pi square into 2m l square. So this is the wave equation. I just want to briefly mention that here this potential energy 0. So because of that we consider that equation 0, v is equal to 0. But outside this barrier, outside this the potential energy is infinitive. So this is infinite barrier. So we have to keep it in mind. So from this equation we also conclude that the energy level of one dimensional box or one dimensional system, that it will produce the discrete energy levels. So that means this is the quantized energy level. So now these are the equation from 1D box. So you can apply this in one dimensional quantum oils. So you apply when you get any quantum oil which the length is L. So this length is considered the 0 to L, this one the 0 to L, inside this potential energy 0. So you get the wave equation like psi x is equal to A sin kx and kn is equal to n pi L. This is quantized because n is there, and you also get the quantized energy levels. So you have to note it here that the confined electron have quantized energies. The first one is confined electron have quantized energies in the quantum wells. The second one is the smaller L. That means when the length will be small, then what will happen? That lead to higher energies. So this is, you see that this parameter, if the L will be that means that gap between the energy level, this gap between the energy level will be higher. So one parameter more, that M lighter masses, that means leads to higher energies. Also, if the mass is small, then you get the difference between the energy level, more gap between the energy levels. So from your previous knowledge, you can also normalize this wave function. So for that, you see this is the normalization condition, 0 to L psi star x psi x dx is equal to 1. When you normalize it, your function, you will get the A is equal to root 2 by L, and your normalized wave function is root 2 by L sin kn x. So this is the equation from this quantum oil of length L. This is the normalized wave equation. That means this is the normalized wave equation for this length L. Now, how you calculate the carrier density in quantum oils? So for that, you already know from your previous knowledge that the here carrier density means the probability of finding the electron. So this is Px proportional to the psi star x psi x, or you can you get the your wave function is this one. So you apply it here. So Px proportional to sin square kn x, and that means Px proportional to sin square n pi x pi L. So this way you can get the probability of electron inside the 1D quantum wells. That means your electron is confined in one direction, maybe it is confined in Z direction. So now you also know the features of your subband of this quantum wells. So this is the px, this is the I already told you, this is the carrier density in the quantum oils, and when you plot it with the x means length px versus x, so you will get this type of features like particle in a one dimensional box. So this is the when subband is n is equal to 1, so that is sin square pi x by L. So and in the middle of this you will get the maximum probability of your particle or electron inside this quantum oil. So that means your length will be here L by 2. So then you will get the maximum probability of the electron. Now when your subband is 2, n is equal to 2, then you again apply this equation and calculate the carrier density. There here is sin square into 2 pi x by L, and you will get a node in here. This is the L by 2 length, and in this case you will not get the electron in the middle of this quantum well. That means here you will not get the electron. So that means you will get L by 4 length here and here. So in this way you can also explain the probability of finding your particle or electron in quantum wells, 1D quantum wells. Now, how you practically produce quantum wells? So this is interesting things that previously you applied this quantum mechanics to solve the classical problem, but you can also develop a device where you can also you can get the quantum confinement effect. So this is the one of the first example where quantum confinement effect observed. This is by electrostatic method. So this device is fabricated by electrostatically, so where quantum confinement effect was observed. So now how you develop this device? That this is a p-type silicon, and then there is a layer of silica here, and then one insulating layer. In this way, this device is fabricated, and above of this there is a metal plate. Now, when you applied positive voltage to it, so what happened? If you applied positive voltage on the above the top of the metal plate, then what happened? That lowered the potential energy of the electron. That means this positive voltage lowered the energy of the electron in the silicon. So, and then what happened? That this positive energy also attract the negatively charged electron, and then this electron will pile up here. This electron in pile up between the silicon and insulating layer. This is silicon and insulating layer, and that will actually generate the electrostatic confinement. And then from this you can also see that the electron is confined in the z direction, and it can freely move in the xy plane. So now we will see that and we will apply the quantum mechanics here. So this is the triangular quantum well energy level. This is somewhat different from your normal 1D problem, like that there is, you see that cubical energy levels, but this is somewhat different, and this is somewhat complex. In normal 1D box, you apply 1D box or 3D box, you use the quantum mechanics in a very simple form. This is simple mathematics, but in this case, this is very complex mathematics is involved. And this way you see that the energy level or discrete energy level is given is this way, this figures. So this show the discrete energy levels of the quantum oils, practically produced quantum oils, and energy level is given by this equation. When you solve this equation, or you get the wave function, when you solve this problem, you will get the wave function, ARE wave function, and the type of ARE wave function is given here. So this is somewhat similar, somewhat like that, and that is also penetrated outside the length of these quantum oils. So now we have to understand what is the infinite and finite quantum well. Generally, in case of 1D box, you see that there is an infinite barrier, but when we produce the practically quantum oils, in case of which we get the finite barrier, uh, not that is not a infinite barriers. That means your electron will still have quantized energy level, but the electrons are able to leak out little bit. So in case of that, you can see that when you confine electron in a 1D type box, there is a 0 to L, and inside this Vx is 0. So you see that you see this type of wave function. So in case of infinite, when there is a infinite barriers, and your energy level also given by this. But when your practically developed quantum wells, you see that your waves is leak outside, you can see. So in case of the finite barriers, but this is leak out somewhat outside, but it have still quantized energy levels. You can see this area, there is a quantized energy levels. So from that we can conclude that in this case confinement is little bit less, and also the electrons can leak out. They are not so confined as tightly. That means energy will be little bit lower. So now we can also practically we can produce the quantum wells in case of heterostructure. This is the typical heterostructure. You can see here that in this case that this heterostructure made up of aluminum gallium arsenide and gallium arsenide and aluminum gallium arsenide, the layer of. So first layer is aluminum gallium arsenide, and then there is a 10 nanometer to 20 nanometer thickness of gallium arsenide, and then again there is a coat of layer of aluminum gallium arsenide. Actually the aluminum gallium arsenide has a band gap little bit bigger than the pure gallium arsenide semiconductor. uh, and when you when you grow this type of structure, you will see the quantum confinement effect in this region. So that will also produce the quantum well in case of the gallium arsenide. And in this case, I have to also mention that electrons are confined in the z direction, but the electrons are free to move in the xy plane. Now the question is, what will be the wave function psi x y z in this case? So we have to check the wave function in this case. So generally we apply this 1D box, this type of wave function. This is minus h cross square by 2m d2 psi x by dx square plus vx psi x is equal to e psi x. But in case we have to apply the three-dimensional wave function in this case. So how you apply this three-dimensional case? Just you have to change this one to delta psi. You see it here. So this is minus h cross square by 2m delta psi xyz plus vz psi xyz into E psi xyz. This is the typical equation for this heterostructure quantum well. And you also know that how to solve this wave equation 3D wave function. So you apply the separation of variables and then you can solve this wave function. So when you apply the method of separation of variables, and in this way you get the separate wave function for that, and the wave function you will get this one psi x y z. This is proportional to the plus minus I k x x into e to the power plus minus I k y y into phi z. So here I actually your electron is confined in z direction, but your electron can freely move the xy plane. So for that reason you see that this one shows the plane wave propagating in the x direction, but this one showing the plane wave propagating to the y direction, and this one the your electron is confined in z direction. So that will a different function in the z direction. That means the direction in which the confinement occurs. So you will get the wave function for the confinement effect. So here you can apply your quantum mechanics concept also. So this is the short form of this equation psi x y z. This is proportional to the e to the power plus minus I k parallel vector into rho into phi z. Here I already mentioned that psi rho is a position vector in the xy plane. So well, so now another example of practical produce 2D electrons. In this case, you see that now we consider the quantum well where electrons are confined thinly. So you see your this is the length of L, and your electron is confined this direction. That means this is z direction, and your electron can freely move in the xy plane. This xy plane, this your quantum this xy plane, and your electron can freely move in this case. So now the question is, what is the electron wave function in this region? So how you define this wave function here? So this is psi r. This is approximately I k r r, and you can write it as your wave function is your electron is confined in z direction. So you can write sine k z z into e to the power I k x x into e to the power I k y y. So this is due to the a plane wave from x direction, and this is due to the plane wave of y direction. But this represent your wave function for the quantization, so for quantum, because of the quantum confinement effects. When you normalize that one, if you normalize your wave function or you normalize in xy this region your electron, then what will be the wave function? This is root 2 by L, because you confined in the z direction your electron. So you will get root 2 by L sine kz by z into 1 by root a e to the power kx x plus ky, and this a represent the area normalization area of xy plane where your plane wave of the electron propagating. So you also get some important feature here. You can also get the subbands here. So this is the wave function. So for this I already mentioned that psi r sine k z n z e to the power I k x x, and this is I k y y. So this is the equation that you already know, that k is a quantized quantity, and your energy En, where confinement effect observed in, that means in this z direction, your energy it is given by En is equal to h cross square n square pi square divided by 2m L square. And this is a, you can say that this is a discrete set of energy level associated with that confinement in the z direction. So what is the total energy of this system? You can get from this equation that E is equal to En plus h cross square k square pi parallel k square divided by 2m L square. And this energy is due to the kinetic energy in the xy plane, where your electron behave like a, your electron wave behave like a normal wave, or just a minute, plane wave, sorry, your electron behave like a plane wave. So this is the total energy of this system. So this is the features of the subbands. So if you plot energy versus wave vector in the xy plane, you get the discrete levels that come from the confinement in the z direction, and you also get some additional energy that come from the motion of the xy plane. So this is, you see, this is the energy equation in the z direction, Ej. So sorry, this will be En is equal to h cross square n square pi square by 2m L square, and k parallel you have to give by this k x square plus k y square. Or total energy is given by E is equal to Ej plus h cross square k parallel square divided by 2ml square. And the wave function is given by this equation, psi rho e to the power I k parallel into rho. And this is the discrete energy level. You see, this is the discrete energy level generated by the, because of the confinement effect. And this confinement effect explain the different phenomena, electrical and optical phenomena in different materials. So now the conclusion. So you already know that quantum mechanics, the theory part. So you have to understand that quantum mechanics is a fundamental theory which is extremely practical. That means you can apply this theory or quantum mechanics in various cases like quantum wells, quantum wire, quantum dots. They explain the exciting optical and electronic properties of the semiconducting materials. So this is one of the important features of the quantum mechanics from the classical where mechanics. And also you can also generate or develop the quantum confinement, and you can practically produce quantum confinement in different type of materials. I have already mentioned 3 examples. This is the p-type semiconductor device where you see that how quantum confinement is observed. This is another, this is quantum oil 3D, and this is the 2D where quantum confinement is observed. That way you can explain various phenomena, various uh, various thing using this quantum mechanics, and you can apply it practically. And this material have a huge practical application and a huge practical market also. So finally, I would like to acknowledge that the presentation is designed being inspired from the teaching of Professor Mark S. Lundstrom. He is a Don and Carol Cypress Distinguished Professor of Electrical and Computer Engineering, Purdue University. Thank you.